Thanks so much for the introduction, and thanks for the invitation. I used to come to IPAM when I was a postdoc at Caltech a lot, and this is the first time speaking, so it's a pleasure to be here as a speaker. So I debated a lot what to talk about, because I have been doing a couple of things in this domain, and I decided to talk about two different things. It's kind of totally different. I will focus on this one first, which is a sample complexity analysis for a traditional linear system identification method called Ho-Kalman. And I saw there were lots of roboticists in the schedule. Most of them are not here yet. But I will also talk a little bit about inverse constraint learning. So this is something we started doing recently. And there are some optimization questions there. I want to get some feedback from this community. But I will start by giving an overview of some of the problems that I work on and some of the things that I am interested in. And maybe they will lead to some discussions later on. So I will be around all through the week, and I will be happy to talk about these different topics. So I work on control of safety-critical autonomous systems. We are doing things with autonomous vehicles. If you're at Michigan, it's impossible to avoid doing things with cars. And we are also looking into some autonomous aerospace systems. Here is a simulator where we are trying to autonomously taxi an aircraft. And we want to give certain guarantees on the behavior. And we can give these guarantees only when we have models, which is not really, which doesn't resonate well with learning. When I get a little bit more adventurous, we also try to put these things on real vehicles. And when you start putting these things on real vehicles, you face this unavoidable reality that your models are not good enough. And there's always a model mismatch between what you designed for and what you developed, your proofs and everything. And you need to somehow overcome that model mismatch, and we still want to give some proofs when we implement things. And one other thing, I also collaborate with domain experts in different domains where we have tons and tons of data. But these are not simulation data. These are like, for example, in the context of smart grid, you have data corresponding to behaviors of these thermostatically controlled loads on-off switches of certain devices. And these devices can be used for demand response if you can control them. Or in the context of driving, you have people driving on the road, and you have data from that. But since you don't have the simulator here, the challenge in terms of learning, especially learning policies in these domains, is that you cannot get on-policy data. So you learn something, but there is no way to understand how, when you put that thing in the real system, if you implement it, how the other agents in the system will interact with what you learn. That's why I usually like models. Even if I have data, I want to go from data to models. Then if I have the model, I know how to do control, and I know how to do a couple of different things with the models as well. So in the context of from data to models, the problems that I study is system identification, model invalidation. You have a model, you collect more data, you want to figure out whether that model is good, or fault anomaly detection. So you are collecting data, maybe you have a model of the system, and at runtime you want to figure out whether this model is a valid representation of your reality, or if something changed in reality, whether you can detect that using this model. On the model to control part, the types of control problems that I am interested in is on the algorithmic side, and they are typically decision problems of this form. Does there exist a control policy such that something holds? And the something could be stability, some inductive invariance, or some constraints or time-varying fancy constraints written in temporal logic. So typically, I want to solve these type of constraint control problems. So things that I like, I like models, and I think one useful thing about learning is you can get models, because I know how to ask these decision problems when I have a model. Does there exist a controller that does this for this type of system? I don't know how to ask these type of questions for data. If I have the model, the other ability I have is I can change my control objective. I can change the question, and I can re-ask the question, and I can still use that model. That's why I like models as well. And if I get more data, I can check the validity of my model. But I don't know how to validate a policy against pre-collected data. So that's another reason why I like model. I know how to validate models against pre-collected data. I don't know how to validate policies against pre-collected data because the other agents in the system might be reacting to my policy, and pre-collected data does not capture that. And the other thing that I like is constraints, rather than cost functions and objective functions, because specifying a task with a single cost or reward function is in general hard, and constraints are, for me, more modular. And since I work on constraint control, constraints are more natural for me as well. Yes?
I don't know whether you want questions now or later.
What's that?
You want questions now?
I can take questions now.
So the very first item strikes me as a bit odd. So if you start with data and you derive your model, then you can ask these questions about the model, but since you started this data, you didn't have a model, you just derived the model, maybe be relevant or irrelevant to the actual control problem. It's like maybe you can answer those questions, but does it mean anything?
That's totally true. So this is the case that doesn't involve learning. If you give me a model, I know how to answer these type of questions. But one other thing that I know is that if you give me extra data, I can tell you, oh, this model is good or not. But it would be very interesting if you know ways of doing it. I would be interested in hearing is, you have data, you have controller, you say something. But I am not claiming I can, finding the model, I can answer this question. But if by some magic I have a model and I know something about the accuracy of that model.
Yeah, I'm just wondering why you like this.
Because I study control all through my life.
Is it physics-based models that you like, or is it data-driven models? Something that maybe...
Give me the model, I don't care where it comes from, as long as that...
What is model?
It's something that looks like this with a small enough state space. So not a neural network or not a simulator. Okay. So there are a few things that I am working on recently in this domain where we combine learning, control, and optimization. I won't have time to talk about all of them. I will talk about some of them. One is this non-asymptotic analysis of learning linear systems. I will motivate it more. So that would be the main chunk of the talk. I did quite a bit of work on identification or learning of hybrid and switched linear systems. These are, again, linear models, but they switch mode in time. So that was my PhD thesis. And we still keep working on variants of that. So we were doing it batch. Now we are looking into doing it more online. And the other thing that we started looking into recently is a variant of switched systems is when your switching is driven by a Markov chain, where in that domain people looked into model reduction for Markov jump linear systems, where they are trying to reduce the continuous state space, we are looking into problems where we try to reduce the discrete part of the chain. And we are looking into some reduction problems that involves a little bit of learning as well. If you don't know your chain and you are estimating your transition probability metrics from data, what you can do. And this is something fun we have been doing recently, more in the context of robotics, learning constraints from demonstrations. And if I have time, I will talk a little bit about this problem as well. So it will be a bit disconnected, two parts, but this is kind of the plan. And if you want to discuss any of these problems, I will be around all through the week, as I said. Okay. So as I said, the first thing I will discuss is sample complexity analysis for linear system identification. And I will focus on a specific, well-studied, widely used linear system identification algorithm. So the way I see system identification is there are like two different camps here. One camp is you have this complex simulation models, you have ability to generate lots of data offline, or you have the ability to run lots of experiments on this system. Then you are typically in this big data regime, and you want to use system identification to learn some control model, simple model that you can do control. And with that control, you can do all sorts of things that we control people like to do. So this is one setting that's studied a lot. You have lots of data, so you are interested in asymptotics of the type of algorithms you have. And the other regime I call this small data regime, where maybe you are exploring an unknown environment, you don't have that much time to collect this data, you don't have that much time to run one experiment after the other, you have no idea about the environment to create a reasonable simulator, or you are in flight on an aircraft, something blows up. You don't have time to run experiments and figure out what's going on. So in this case, you have very small data. You want to learn what's going on online, and you want to do this at runtime. And possibly with this learned model, you want to adapt and repurpose your mission objectives or whatever you want to achieve. And I am more interested in this talk, this small data regime. And I will start with one system identification algorithm that's developed originally for the big data regime and analyzed for that regime. And I will try to analyze it for the small data online learning setting. Okay, so we will try to learn linear systems, simple, your A, B, C, D matrices, driven by some input. I will pick this input to be Gaussian. And there's also this unknown process noise and measurement noise. So in the asymptotic analysis, this is the well-studied parting control. You ask the question as n goes to infinity, where n is the number of data points that I collect over time, my time horizon. Or as noise level goes to 0, can I learn this system model? Or given an algorithm, how does the algorithm behave as n goes to infinity and or noise goes to 0? So in the non-asymptotic setting, what we want to do is, given this finite amount of noisy data and some properties of this noise terms, how does my identification accuracy depend on the data size n and the properties of the noise? So this will be the type of question I want to answer for this type of models. And what can be the best identification? What is the best that can be achievable in this setting? So there are results in both domains. As I said, this is the most classical system identification setting. So go take any textbook on SysID. You will find tons of results on this. And there are also well-established and fairly commonly used techniques out there. One is Ho-Kalman, or eigenrealization algorithm. That's another name for the same thing. There is enforced. It's a subspace identification method. And there are various others. So you can take your MATLAB SysID toolbox, and it comes with a suite of well understood in the asymptotic regime identification algorithms. In the non-asymptotic setting, there are also results both from control community and more recently from statistical machine learning community, where control theoretic results are not specifically for these algorithms. They have certain assumptions. So, for example, one of the assumptions they have is something called noise invertibility, which roughly means from your data, if you observe, if you know the actual system parameters, you can uniquely solve for the noise. And in that setting, there are quite many algorithms out there that analyzes sample complexity. And this paper is a recent paper that gives a review of existing results. And it also has some new algorithms for this specific domain where you have noise invertibility. And there are recent results also in the machine learning community, mostly Ben's work with a couple of co-authors. And what we will do is similar to this, but the difference is that most of these results are for the case where you observe the state rather than an output. So it's kind of analyzing a time series dependent least squares type problem. But what we want to do is we want to do analysis of a method, an existing method, rather than coming up with a new method. And we want to do it for input-output data, rather than from an ID point of view, simpler setting where you observe the state. Although from a statistical analysis point of view, observing state doesn't make things too easier. Okay, this is the plan. Any questions so far? Okay. Okay, so let me list what our contributions are for before telling you the details. So what we did is we picked this Ho-Kalman algorithm. I will tell you what Ho-Kalman is. And we tried to understand its noise sensitivity and robustness. And based on that, we gave a sample complexity result, which gives you some provable guarantees on the accuracy of the learned model. And some of the properties of Ho-Kalman, as I said, it learns from input-output data, so no state measurements. This problem is generically ill-posed. I will show you why it is ill-posed, but if you're a control person, you already know. And this is from single trajectory, so we are observing the data and we are learning at the same time. We don't have the luxury of collecting multiple trajectories where I might have statistical independence. So I want to do everything from the single trajectory. And as I said, this class of models I am interested in does not satisfy this noise invertibility property, so I cannot use existing results from the control community. So identification problem, as I said, in the noiseless setting, it's ill-posed. We can only learn up to a similarity transformation. So this might be clear to some of you, at least control people, because if I just redefine my state with some invertible matrix P, this model will generate exactly the same input and output as long as I change my initial condition from x to x tilde.
Why do you call this ill-posed? I mean, somehow the transfer function, which is what you really want to identify, is well defined, right? So
yeah, but learning ABCD is ill-posed. You don't learn ABCD.
Yeah.
So I have a reason when. Yes, I have a reason. So there are problems where you really want to learn ABCD. For example, one problem we are looking into is you have structure on A.
That's a different, yeah, sure.
So that's the mindset I am coming from. That's why I am calling this is kind of ill-posed. And even up to a linearity transformation, I can only learn the controllable, observable part of this system. So if there's some uncontrollable or unobservable modes, I won't be able to learn them. And we will assume the system is controllable and observable. And this will pop up in some of the results, how uncontrollability or unobservability can hurt you. Will pop up in the results. So Ho-Kalman is a two-step procedure. Yes.
So in the last equation, noise is gone?
In both noise. What's that?
Yeah, like previously we had WT and VT or whatnot.
So the noise is gone for now.
It will come back?
It will come back. So the thing is, actually, Ho-Kalman, if you go to the original paper, there is no noise in the original paper. It came back, and when it came back, they started calling this eigen realization algorithm. So,
and this observation about unreliability or like ill-posedness with the P, it transforms the noise covariance matrix as well, right? So it's like you can't really assume that
so that's a very good point. Actually, that's something that bothers me in our analysis here. We didn't submit the journal version. Maybe I shouldn't reveal all the weaknesses of the analysis. But one information we don't use, let me come back to that. Ask me if I don't come back to that. So we are assuming a noise covariance, and there's extra information in the noise covariance that sort of messes up this ill-posedness or learning up to a similarity. So you can possibly extract a little bit about that similarity transformation by looking at your noise covariance. But we are not dealing with that. Okay, that's a very good point. Okay, so this is a two-step procedure. So the first step is you learn the so-called Markov parameters of your system. Markov parameters of the system is D, CB, CAB, CA square B. And if you have, for example, a single input, single output system, this is essentially the impulse response of your system. And if you look at the transformations that I showed you for ill-posedness of the problem, these Markov parameters are invariant to your basis function. And once we estimate these Markov parameters, what Ho-Kalman does is it estimates the Markov matrices from these. It estimates the system matrices from these Markov parameters. So that would be the second step of the approach. I will flip things a little bit. I will first talk about how to estimate the system matrices from Markov parameters. Then I will show you how to get the estimates of the Markov parameters. Okay. So assume someone gives you the Markov parameters. Then you form this block Hankel matrix. Hankel meaning this anti-diagonals are constant, and you fill these anti-diagonals with your Markov parameters. And if you look at this Hankel matrix, one thing you will observe is that it's a multiplication of this matrix with this matrix. And if you're a control person, you will be able to tell what these matrices are. This is your extended observability matrix, and this is your extended controllability matrix. And if your system is observable and controllable, we know this is rank n. If I have n states, this is rank n as well, and you will get this to be rank n for n-dimensional state spaces. Then what you do is you define this H plus by ignoring the last column. You define the H minus by ignoring the first block column. Then one thing you can observe is that H plus is some observability matrix times some extended controllability matrix. Then you can write H minus as that extended observability matrix times A times Q. Once you have that, if you have H plus and H minus, you can essentially, you have this one, you have this one, you can solve for your A. And the way you do it is, we know this thing is rank n. So any properly sized submatrix of my possibly infinite Hankel matrix is rank n. So your L is, you do an SVD. This is exact since it is rank n. Then you set your observability matrix to be U times square root of your singular values. You set your controllability matrix to this. Then first m rows of your observability matrix. Remember, it starts with C. You take it as your C bar. Last p columns of Q, first p columns of Q becomes your B bar. Once you have these O's and Q's, since you have H minus as well, you can solve for your A bar. So in the infinite case, if you do this truncation, the diagonal entries here, non-zero singular values, are called Hankel singular values, and they are related to many interesting properties of your system, including its H infinity norm, and you can also use them to do model reduction. And these A, B, C, D matrices are called a balanced realization of your system. Balanced in the sense that you put your system into some basis where each state is as observable as it is controllable. And the smallest non-zero singular value of your Hankel matrix tells you how identifiable your system is. Smaller that value, it's harder to identify, because there's a mode that's equally unobservable and equally uncontrollable, or it's not actually uncontrollable or unobservable, but its observability is really low. And this tells you the smallest non-zero singular value there tells you about identifiability. Okay, so we said that was what you would do if you had exact Markov parameters, but we said we will estimate these Markov parameters so they won't be exact. But we will do more or less the same procedure. Instead of the true Markov parameters, I will just plug in whatever estimates I have. Now, instead of an exact SVD here, I will do the truncation, and I will do the same thing. So one question we ask is that if I have some error in my estimates of A, B, C, D, or my estimates of Markov parameters, how does that error propagate through this weird process of doing SVDs, doing weird pseudo inverses, and stuff? So the question we will try to understand is, given a bound on my estimate of G, how good is the estimate of A, B, C, D that I have? So one thing we can show, since H is essentially sticking the values in G in a matrix form, you can bound the error in H based on the error in G. And you can do the same for L, which is just the SVD of H. And this T1, T2 is how you choose the size of your H. How many columns you have, how many rows you have. And this T1, T2, they should be larger than n, so that you get at least rank n when you do the SVD. Then if we also assume this L minus L hat which is the low-rank approximation of my H, satisfies this property. Remember, this minimum non-zero singular value is telling me how identifiable the system is. Then the C, B, and A that we compute satisfies this, where P is a unitary matrix. And again, if my system is less identifiable, this number will be small. My errors will be large. If my system is identifiable, this will be a small error that we get. Now,
That doesn't seem to relate to the balanced realization that you have. If the system ID algorithm has an explicit goal of giving a balanced realization, then might you get tighter bounds and you couple the A and C, for instance?
so this is taking into account the balanced realization in the following sense. This is not an arbitrary singular matrix. This is a unitary matrix. So I am restricting the class of matrices that I use as a transformation here. And the other thing is that if you do this process to a noisy Hankel matrix, you are not guaranteed to get a balanced realization. If you do it for the real ABC, you get the balanced realization. I think in general, you don't get a balanced realization if you do it to the noisy matrix. I don't know if that answers your question. Okay.
I don't understand the statement though. So this is B is going to be unitary.
Yes.
Not the general coordinate transformation, right? And this is with respect to a particular realization.
So this is the true balanced realization.
What do you mean by true in this case? I mean, there's many true things that I could.
So there is the true system, noiseless.
But what do you mean by that? I could pick another realization, right? But I know.
But their balanced realization will always be the same.
Sorry.
If you have any
A is balanced or
A bar, B bar, C bar is the balanced version of the true. Okay. So if we can get estimates of the Markov parameters, we know what to do. So the question is, how do I get estimates of my Markov parameters? And here, what I will assume is that my initial conditions is 0. If it's not 0, you just have a few other terms, but the analysis goes through. I am deriving the system with a Gaussian, but I exactly observe and know the values of this U. And the system is also driven by this process noise and measurement noise. They are also Gaussians. I know the variance, but I don't observe red stuff. So I observe U. Then cross correlations of input and output will give you your Markov parameters. If we had multiple trajectories that are independent, then I could estimate this expectation just by averaging across trajectories. But I don't have that luxury. I have a single trajectory from my system, so that doesn't work. I need to do something a little smarter here. And for that, what I will do is I will consider n subsequences of my data, each with length t. And I will try to write my output at time by t in terms of the past capital T measurements, past capital T inputs, and the initial condition at, in this case, x0. Then I will try to write this guy in terms of this, and this one, and so on. So I can just open up a linear systems, discrete time linear systems book, And I can write my yt in terms of the initial condition or the condition t steps past my current input, my previous inputs in the last t steps. And there will be some effect of the noise terms, and there will be some effect of the measurement noise as well. And I will just rewrite everything in matrix vector form. I will just stack together my inputs, stack together my noise terms, and I will call this effect of the initial condition as ET. So we will characterize the statistics of this guy and treat it as noise. These are noise terms. I already know the statistical properties of these things. These are IID noise terms. And I want to estimate this G. And to estimate this G, given that these are all noise, I will do least squares. So this is what I will do. I have yt. I have n of these chunks over here. So I will minimize the sum over all of these chunks. I have one equation per chunk that I have. I have my u's, and I will try to estimate x using this process. And this is simple least squares I can solve in closed form.
The matrix F also consists of these unknown matrices C and A. So you do know the noise of W, but you don't really know the noise of F.
F includes the CA square type terms. F doesn't have any noise in it. F has my system parameters. F doesn't have any noise. But F is something I don't know.
Exactly.
Yes. So one thing that will happen is that F is essentially, let me see. F is something like observability metrics shifted around. But F will pop up in my analysis as a term.
Well, just regarding that, isn't least square just like rejects all this noise, like it gets rid of the, like takes expectation over the noise, effectively. Filters out the noise, that's why it's gonna work.
That's why.
You treat it as noise, you treat it as, if you take condition expectation of all of this, and so that. Right?
Yes, I didn't quite understand what you are saying, but yes.
And I think the question was, why does least squares work?
Yeah.
Why does it work?
What?
I think, why wouldn't it work?
Because it's not maximum likelihood in
Yeah,
it
but why do you need maximum likelihood?
to justify it.
Yeah, but why do you need it? You can prove
No,
it
least
works.
squares works where the errors that you have
No, this is a,
had a condition expectation of 0,
This
and
is-
they have
that's a synthetic
That's-
condition.
So I don't know. You might.
this holds actually here.
What does it mean? It holds.
What?
What does it mean? It holds. What I will claim in the end is that if you do this, I can give you a sample complexity bound. I don't know if you do maximum likelihood, you will get a better sample complexity bound. That I don't know. But I will just do this, and for this I will give you a sample complexity bound, and I will claim it's not too bad. Okay. So the question I will try to understand is, I am doing this least squares. Maybe it's not the best thing, but how good it is. And it won't be too bad. So this is kind of the result. If you pick your n large enough, roughly growing linearly with t, and your other system parameters, inputs and outputs, with very high probability, the error of this estimate looks like this. And this is your input. So if you have large variance of the input, your signal-to-noise ratio increases, so your estimation error decreases. If your noise terms increase, your estimation gets worse. And if your number of samples increase, your estimation gets better. As your number of samples increase, your estimation gets better. There's a more refined version of this result in the paper where observability, controllability gradients pop up over here of the original system, but this is a simplified version.
So n appears in both sides. N will equal something.
Yes, and should be larger than its log. So the reason that happens is, I can give you some insight if you want. The dependence on t is a little weird. Because there are things that improve with t. For example, as t grows, the effect of my initial condition, I have a stability assumption on A. I don't know if I stated that somewhere, but I am assuming A is stable. As t grows, what happens is that the effect of the initial condition shrinks. So you sort of get rid of this term as t grows. And one other thing that's happening here is that we are kind of doing at some point a FIR approximation in a sense. And if you have a low order model, then FIR is a bad approximation. If you have a high order model, FIR is a good approximation. You can take order log and FIR coefficients and it would work. That's the reason why you need this n and t. That's the reason why n is appearing on both sides. Yes.
Does f depend on t? Normal f? Does it get bigger as t grows? I can't remember. It's on the previous slide.
Yes and no. So f itself depends on t. But one other result that we have is that since the system is stable, the tail terms on f are going to 0. So you can essentially set those tail terms to 0, and you will get rid of the dependence on t. Yes.
Would this result still hold for closed loop?
What would change in closed loop?
Nothing much, right? Like UT would depend on the observed quantity. So I feel that it should hold as long as there's some persistence of excitation.
If I have additional persistence input with which I am exciting the system, I will learn the closed loop dynamics, possibly.
I just want wait.
But the thing is, sorry, if you have state feedback and close the loop, if you have output feedback, how do you close the loop is a totally different. What's that? So, like closing the loop, but if you assume you have kx as your.
Well, I was thinking about output feedback.
With output feedback, I have to. It gets a little. It gets a little weird. I haven't thought about it. It's weird. Yes.
I see S of u is at the denominator, which means that u is non-trivial. How common is it that people will let you inject Gaussian control onto their system?
That's a very good question. We tried it in the lab. It's a terrible idea. Yeah, that's a good point. I don't know practically for what. I think it also depends on the system. So if you have something like biological systems or things that blow up or things don't crash, you can inject Gaussian. If you have things that blow up, things crash, don't do it. We are looking into, so one thing actually we are looking into is, can we somehow close the loop with a controller and add something, but we don't have any results on that yet. So I have 5 minutes left. I didn't come to the.
We had lots of discussions, so you would.
Okay.
Time for your talk.
Okay, so you can combine this and you can say, given some delta and epsilon, we can find a tight enough n such that if we have input-output data of length n bar, with probability 1 minus delta, we can estimate the system matrices by accuracy at most epsilon, or you can give me the bound, and I can tell you how much data you will have to achieve this type of probability. There are a few extensions of this that I didn't talk about. You can get estimates of the H infinity norm. With this process, you can tell things about your infinite Hankel metrics, how well you are estimating the singular values of your infinite Hankel metrics, from which you can tell things about system order. You can use your Markov parameters as an estimator, like Kalman filter, to figure out what your next y is. And you can give error bounds on that estimate as well that uses Markov parameters. So those are some extensions. I have some numerical examples. And we compared this. So there's this other idea to simplify the statistical analysis where I said if you have independent data points, analysis is a little easier. So you can separate your chunks and treat them as almost independent. But this is not making most efficient use of your data, and this is not what is done in practice. In practice, this is what is done. And you can see that if you don't have any separation, you get much faster learning with a number of data points. So it uses practically better use of data with still giving you tight statistical bounds. So I have more numerical examples showing the effects of noise variances, both in the H infinity norm error, and I don't have those. I also have things that shows how well you estimate your balanced realization ABCD matrices. Okay, so I didn't have too much time to talk about this, but I can show you some. I can show you the main idea, and I can stop after that. So this is going to be very different, but we got interested in this, and I said I like constraints more than cost functions. And we were like, oh, there's inverse optimal control, but I don't like reward functions. Can I learn constraints using similar ideas? As I said, constraints are more modular and explainable. I forgot who said that, but I heard it in a talk. Humans don't think in terms of objective functions. And if we can somehow learn constraints, we can use them for control design. But one challenge here is that we will try to learn things from only positive examples, so we don't have this classifier type property. And there's lots of work also from people in this room on learning these things. We have demonstrations. We assume we have demonstrations from possibly different tasks with common constraints. And we came up with two approaches to solve a simple variant of this problem. So let me tell you what demonstrator does and what the problem we are trying to solve. Demonstrator knows the cost function and knows all the constraints. We know the cost function. We know the system dynamics. Maybe we know control constraint, part of the constraints. And demonstrator solves this problem. And we assume there's a parameterization of my constraints. So known possibly task-dependent cost. Known possibly task-dependent constraints. For example, if you are trying to reach from one point to the other, these could be your start and goal points. There are some known shared constraints. So if you have torque limits that you know, they are shared all through tasks, and you know that. And this is the unknown constraints shared across demonstrations. And our goal is to try to learn this from optimal demonstrations. We assume someone solves this problem for possibly different goals and target positions, and we will try to learn that. So we have two different approaches for this. In one, if you have globally optimal solutions, one simple thing you can do is, if you can generate any trajectory that has lower cost, that satisfies everything that you know, that violates your constraints. So there's a very efficient way of generating negative examples using optimality. Then you can cast this almost like a classification problem. The other thing that we thought about, maybe you don't always get globally optimal demonstrations, but you get locally optimal demonstrations. In this case, your demonstrations should satisfy the KKT condition. And even if your dynamics are nonlinear, since these trajectories are known, this is usually a well-posed problem. And in both cases, you can write down mixed integer linear programs for depending on the constraint parameterization. But if your constraint parameterization is easy, you can try to extract your constraints with that. So this only tells you this only gives you one feasible constraint realization. You want to find constraints that are valid across all possible such realizations. And we have ways to query those as well and extract volumes of guaranteed safe and unsafe regions. And we have some geometric analysis of, this is an ill-posed problem, when you can learn what type of things. So we have some fun examples where here what we are trying to learn is that there are these demonstrations with this 7 degree of freedom arm, and it's avoiding this elliptical constraint. And we can learn that elliptical constraint from a few optimal demonstrations, and we can do planning. Here is our bartending example, where there are pose constraints. You don't want to spill the beer or milk. There are obstacles that you want to avoid. And we can, in this case, we don't have optimal trajectories. We use a VR setup where human gives demonstrations. And we can learn, again, constraints fairly accurately that we can plan with them. And there's a quadrature thing as well. I will tell one other thing. So we tried doing this for time-varying constraints, and things got a little strange there, because now your forward problem has integer parameters. So what does it mean to be locally optimal versus globally optimal is meaningful. Locally optimal is a little fishy. So if you just say, I am locally optimal for all fixed values of my integer variables, it's not enough information. So we came up with, I won't tell you what this is, but we had to came up with a variant of local optimality for discrete problems. It's a combinatorial thing. And if anyone knows how to define local optimality for discrete problems, I would love to hear. But we have a way of defining that that seems to work. And with this, we can again, here we are learning some temporal logic tasks. So the task says, first press the button, then go take the mug, give the mug to the person. And again, we have some demonstrations with VR, and we can learn some temporal logic constraint of this form. OK, with that, I will stop.